Hello and welcome to the first video lecture accompanying Handout 7. In this video, I'm going to introduce the ideas and key formulas of Schrödinger's equation in a couple of particular situations, and in the second video, I'm going to go over some examples, 3 examples to be exact. Okay, so let's get to this. All right, Handout 7 called the Schrödinger's equation. If you look at the title, I titled it Finding Probabilities with the Normalized Schrödinger Equation. I think that gets to the point of what we want to do. What probabilities are we talking about? The probability of finding a particle somewhere, okay? That's it. Particle might be an electron, okay? So we're talking about the probability of finding an electron at some location within a confined set of parameters. So we're not trying to find a particle that could be anywhere in the universe. Instead, we're trying to find a particle that we know to be in a box or well, and we want to find out what is the likelihood that it is in the left half of the well or the right half of the well, for example. Okay, that's the idea. That's the concrete idea that we're working with today. All right, so let's look at our 2 objectives. So if we look at the first one, it is to understand that the Schrödinger equation is a differential equation that when considered in its time-independent form can be used to find the probability of a particle existing in a confined 1, 2, or 3-dimensional space. Furthermore, we want to understand that these probabilities found for particles existing in a certain confined space are themselves dependent, on the dimensions of the confined space and the quantized energy levels of the confined particle. Okay? So we have quantization of energy, which is completely consistent with the overall concepts that I've been presenting in physics 37, physics 36, regarding what quantization means. It means that there are steps, in this case, steps of energy for a confined particle. I will make this relevant to maybe a system you're familiar with in a moment, but let's not get there yet. Let's start laying the groundwork and referring to things we've seen before. Okay? All right. So first of all, I want to clear up some notation. This is notation that refers to waves and notation that specifically refers to matter waves. Okay? All right, so let's take a look at it. So first of all, we have, and I'll get to these graphs over here in just a moment, but they'll come up in due time. But our first equations I want us to look at are kinetic energy. Okay, so here we have kinetic energy, classical kinetic energy, 1/2 mv squared. This would be a particle. Again, most likely an electron. It's our kind of easily imagined realistic confined particle. Right. All right, v squared. And again, that's the thing about this is it has to be non-relativistic. Okay, but that's it. Last time I'll say it. Anyway, so then what we're going to do is then we're going to do a substitution. All I've done here is change this expression by basically multiplying by 1 in the form of m over m. It's a fascinating or annoying little algebra trick, okay? But the reason we do that is because then we can rewrite this as mv squared in the numerator, which of course is momentum squared, translational momentum squared, okay? So this is the idea that kinetic energy is p squared over 2m, all right? Which you've seen before for E equals mc squared. It's actually comes up with the relationship between energy and matter. Of course, here we're not so much caring about the relationship, but it's in both subdisciplines, right? All right. You might wonder why I'm not just calling it K. The reason is because most of the time when we've talked about particle energy, like the de Broglie wavelength, it was the total energy. There wasn't any potential energy. And that's going to be the big thing that we take away from today is we're going to add potential energy, okay? But since most of the time when you see this form, especially here, when you see E equals hf, that is the total energy of the particle because it's just a free particle moving through space. It might crash into something. We might look at the wattage of how much energy it is transferring to a solid when it comes in contact to a solid. Think radiative energy, like heating something up in the sun. But often that's the total energy, hence the notation, okay? But getting to the wave nature, because this would be squarely in the particle nature of a wave particle, that is a matter wave, like an electron, again, right? But we can also think of that electron primarily as a wave, in which case we multiply Planck's constant by its frequency. We could replace Well, basically you can multiply the top and the bottom by 2 pi. Again, the same idea here. And that's just to do a substitution, because when we have h over 2 pi, we get that constant called h bar, which is just Planck's constant divided by 2 pi. And then we can replace translational frequency f with 2 pi f, which is equal to angular frequency omega, all right? And then what about momentum? Well, momentum we know from the de Broglie wavelength is h over lambda, okay? And then what we can do here is then we can replace the lambda with 2 pi over lambda. And again, I've just multiplied the top and the bottom by 2 pi over 2 pi. And again, don't get lost in the algebra here. It's not terribly important, but I just want to show what I'm doing. And so if I have 2 pi over 2 pi, then I end up with the 2 pi over lambda, which I've circled kind of an offset way with green here. Well, that's something called the wave number. And I'm calling attention to that because that's a constant we probably haven't seen before. I've never really called attention to it, but it sure makes the math look much cleaner. And we really can't avoid it when we write out Schrödinger's equation. So the wave number is simply that. It's simply 2 pi over lambda. It's very similar to the idea of angular frequency being 2 pi times f, times frequency. So wavelength is firmly a translational idea. If you take its inverse and you have something that has units of m to the negative 1, so inverse meters, and since you divide it by 2 pi, you know what the wave number kind of is? It's kind of like angular wavelength. That's not the best name for it, but I think that's a good way of thinking about it. Okay? But the best name is the wave number. All right, so that means that we end up with 2 expressions for kinetic energy of matter waves, okay? And again, this is just laying the groundwork of what we're doing here, right? Make sure that we can think about the constants, right? So any matter wave, such an electron, proton, lepton, muon, right? Whatever it is, whatever particle it is, neutron, is we have h bar omega, that's its kinetic energy, but also h bar squared times k squared, the wave number squared, divided by 2 times the mass is also the kinetic energy, right? Now, why aren't we using 1/2 mv squared? Because it's not a good fit for this material, okay? Of course, it's consistent, right? But we've moved our variables around to have expressions that work in our particular functions, right? Well, let's get to those functions, right? So, we're talking about functions today. Why are we talking about functions? Because we're talking about a differential equation. So let's get to our first differential equation, the general time-independent Schrödinger equation, right? This is not as big as it gets. In terms of like general, because you hear that word, you might think, oh, wow, that's scary. Well, the general time-dependent Schrödinger equation would be the most general expression of the Schrödinger equation. And that should resonate with you a bit because we're talking about waves here. We've seen waves before. I've shown you, especially in the supplement to Physics 35, if you took that class with me. So when you took Physics 37, you saw that we discussed the idea of differential equations and wave equations. We looked at oscillators and we looked a bit at waves, okay? So now we're looking at waves again. We actually saw wave equations when we looked at, again, oscillator equations, but very similar idea when we looked at oscillating circuits. So we have another differential equation here. The solution to it, if it was a wave, would be a solution of functions that themselves are a function of 2 variables. So you'd have a bunch of function solutions to your differential equations, or differential equation, that would be a function of x and t, position and time. But we don't care about the time, all right? That's a whole bag of worms that we just don't get into at all. Instead, we're gonna do a lot with snapshots in time. So if we let t be a constant, then we can talk about the wave varying over space. We can draw that easily. We don't have to have a video for it, right? We can think about what that means. So it means standing waves, well, in a lot of our examples here, okay? And that's it. We're taking a snapshot in time and we're interested in position dependence, a function of x, okay? Now, what is this differential equation? It's got a lot going on, right? Well, it's got some constants up front, okay? And again, this differential equation derives from conservation of energy. You know, because sometimes it feels like we've gotten to modern physics and there's no connection, there's no relevance. We're somewhere distant from everything that we learned in classical physics, classical mechanics. But in fact, we're not distant from classical mechanics, from things like ideas like conservation of energy, conservation of momentum, conservation of angular momentum, and of course, Newton's laws of motion. We're just higher up a tower that's built on that foundation, but it's still there. We're directly above it, we're directly related to it. And that's what this is. This is a differential equation derived from conservation of energy. Okay, so we've got a term right here. We'll talk about what that term is in one of the examples. Here we have a potential energy. Here I'm using U instead of PE, just for terminology reasons. But potential energy as a function of x multiplied by some crazy Greek letter as a function of x. More on that in just a minute. Then we have total energy multiplied by that same Greek letter times x, okay? And here we have a second spatial derivative, so the second derivative of that function with respect to x. Okay, so what's the function? The function is the wave, okay? So if we look here, this is the complex solution, talk about what I mean by that, to the Schrödinger equation. This is a wave function, okay? Now we're going to see one that looks a lot like a wave in just a minute, but this is a wave function, okay? It's just that. Again, it's a wave function without time dependence, so it's a snapshot in time. And the letter, this letter right here, is called, or spelled at least, psi, and pronounced psi, like silent P, okay? So this is lowercase psi if you're interested. Not terribly relevant, but I'll let you know that if you're doing the time-dependent Schrödinger equation, you use uppercase psi, which looks like this, okay? All right, just a little bit chunkier. So that's it. It's a wave. Okay, like a sound wave, like an ocean wave, right? Those are waves, these are waves too. The difference is that those were physical waves that were created by some sort of restoring force. Here we have a matter wave, okay, that is created by, I guess, some property of matter that causes it to exist in a particular space, okay? So the restoring force is the nature of matter, right? But definitely a little bit higher minded there. But we still have a wave, a matter wave, like an electron, okay? Now, photons, right, are waves and particles too. But we're not talking about photons here because we're talking about things that have mass. Okay, so we are only talking about matter waves, not photon waves. Okay? So this complex solution, I call it complex because it's got the letter I, which is the imaginary number I. Okay? I'll mention that in one of the examples in passing. It's actually not going to be the focus of your homework or anything, but that's why it's called complex. Not because it's literally difficult to understand, although it may be. It's just that's what we call complex as in comparison to the term real, which would be without the imaginary number I. All right? So this is an exponential function, but of course it's a complex exponential function. So we can use something called Euler's identity, which then we could rewrite the function, looking over here at the graph, we could rewrite the function as cosine kx plus I sine kx. That's a big identity or theorem in mathematics that relates this complex exponential to a sum of sines with, or sum of trigonometric terms, with one being a complex term and the other being a real term. Okay? Importantly here is that the form of the function we're talking about then is one that has motion, right? So it's got something like acceleration, right? Because it has a wave that is changing with the second derivative, not of time, I guess. So it's not really like acceleration. It's more like it's the second derivative with respect to space. So that the wave is changing with respect to location. And then it's directly related to potential energy and the total energy. Okay? So here, since the potential energy is non-zero, that means there is some finite wall around our wave. Within that wall, there is a phenomenon that you probably have heard of. People talk about this a lot in terms of kind of general understanding of quantum mechanics. One of the things that comes up is the idea of tunneling, a probability of something happening that energetically shouldn't happen. And that's the idea here, is that our wave has a certain amount of energy, but yet it's able to pass through a wall that a macroscopic object could not, with a decreasing probability, an exponential decrease. So that's the idea here, is that this looks an awful lot like maybe a cosine function, but within the potential energy barrier, it looks like a decay function. And that's why it's got this representation as a function that has both a real term and a complex term, okay? And again, mathematically, we're not going to get in those solutions. They're actually well beyond the scope of lower division mathematics, okay? But that's the starting point. Now let's move on to what we're actually going to do, okay? So again, this is the idea. This is a particle trapped somewhere, but not quite trapped because it can tunnel through the wall, right? The quantum tunneling. Now, let's simplify things, okay? This right here is our next function. This is, and this would be, our next equation with solutions that are functions. This is another differential equation that is an equation of waves, right? It's still got our wave function, okay, for our matter wave. But notice what's gone, potential energy. How do we get rid of potential energy, okay? Well, we got rid, whoops. See if I just couldn't remember if I had an arrow. Guess I don't, okay. Excuse me. So we got rid of the potential energy with this pictorial representation, or this graph matches the idea of how U equals 0, okay? Well, u equals 0 would be right down here, okay? It'd be right on the horizontal axis, which I failed to label as x, but this horizontal axis is x, just as it was above, okay? The vertical axis is either the wave function or the potential energy, okay? Now, instead of having a barrier with a finite top to it, right? Because this blue represented a potential energy barrier, right? Those exist, right? Particles have a certain, they bump into something. Can they pass through it? Yeah, but they're less likely to. But here, the particle is functionally trapped, completely fundamentally trapped. There's so much energy on either side of this particle that it's really, really trapped for all purposes, okay? And so then what happens, well now, you know what it really is? Now it's like a wave vibrating on the string of a guitar. Because if you think of that wave vibrating on a string of a guitar, right? Held at one end by a metal clamp, held at the other end by a metal clamp, that wave bounces back and forth, trapped on that string, okay? That's a physical wave created by restoring forces with tension. But that idea is very, very similar, is a wonderful analogy, a very functional analogy to the idea of a matter wave like an electron, like any small particle that behaves both like a particle and like a wave, trapped, bouncing back and forth between two barriers. And just like standing waves on a string of a guitar, there are certain allowed standing waves, right? These are the waves that meet the criteria of having nodes at either ends, right? You got your fundamental, your first harmonic, your first overtone, which is your second harmonic. You got your third harmonic and your fourth harmonic, right? Those are standing waves. Same idea with the matter wave. You can have an n of 1 for your first standing wave. That's the one at the longest wavelength. You have your n of 2, the second longest wavelength, right? The second harmonic, right? Now, I don't really call them harmonics here, but the idea is similar. I want you to remember that we've seen this thing before, okay? And this type of differential equation is the same darn type of differential equation you'd see for those plain old tension waves on a string, okay? Or sound waves in a tube. Same exact thing, okay? Same math, same idea, okay? So this is a particle in a 1D box, right? Because there's only one dimension, just the x dimension, bouncing back and forth as it goes back and forth, okay? Which we call a potential energy well, right? Because it's got sides that are infinitely tall. Well, it turns out that the solution to that Schrödinger equation, right? Because this differential equation mathematically is different, right? It doesn't have that second term. Well, it ends up being much easier to solve. The solution doesn't require some complex exponential, but instead it's just a plain old sine function. Okay, it works. Plug it in. Check for yourself. I don't have it as one of the assignments, but sure enough, right? If you plug sine in there and you take its derivative twice, then you get negative cosine, and then you take the derivative of negative cosine, you get negative sine, right? And so then what you're going to have is then you're going to have negative sine times a negative, so the negative cancels with the second derivative, okay? And then, sure enough, you just get that sine kx equals sine kx, all right? And that means that E must be h bar squared over 2m, but it is, okay? So we're good, okay? This is just showing the idea of the standing waves. So solutions must be standing waves. This is the wave number. Remember, that's just 2 pi over lambda, right? And the idea is that you have to have, these, you can fit like half a lambda, right? You can fit a full lambda inside, but you can't fit, say, like 1/8 of a wavelength inside, because then you'd violate the fact that you have to have nodes at either end. And you have to have nodes because the potential energy barrier is infinitely tall, thus no tunneling. You can tunnel, but only if there's a finite barrier, okay? Furthermore, the energy levels of the nth standing wave are given as this, okay? Now, if this looks similar to energy levels you've seen before, that's because it should look a lot like the energy levels that come from the Bohr model of the hydrogen atom. Because it turns out that model that Bohr came up with and works well for the hydrogen atom is, of course, consistent with the more modern Schrödinger equation. Okay, so that's the idea. That's the idea of quantized energy levels that Bohr came across with some bad assumptions, but that can be correctly ascertained with solutions to the Schrödinger equation, a differential equation, of waves. All right, beautiful. Now, the big idea, right? Supposedly, maybe there's lots of big ideas, but the thing I really want you to work with today, so maybe if you should pay attention, you should pay attention in this part, because this is what you actually be solving, what would be on the final, okay? If I put one of these questions on the final. And that's the idea of normalization, okay? So if we look here, what's going on with this line here? First of all, I have an integral that goes from -infinity to infinity of our wave function, okay? Matter wave, but just a wave. squared, okay, and I'm integrating across space. And I'm saying that that has to be equal to 1. What does that tell me? Well, that tells me that if I was to consider some wave function, and I square that wave function, and then I integrate it across all of x, so all of space, then it must be equal to 1, because that means I must be able to find the wave somewhere. I must be able to find the particle somewhere. This is telling me that my particle actually exists. It can't just not be anywhere from negative infinity to infinity. It's got to be somewhere there. Okay, it's a wave, so its position isn't exactly well defined, but it still must exist. It just must have 100% probability of existing. Okay, now when we have this well, which is completely locked off from the outside world, our negative infinity to infinity, because here this doesn't represent x negative infinity to infinity. The color, if you notice, I've chosen the color to represent potential energy, that this is just the idea that the barrier is infinitely high. And thus, going from negative infinity x to positive infinity x is functionally just going from 0 to L. Okay? All right? And so over here, maybe negative L over 2 to L over 2, the way I drew in the picture. Because you're stuck in a box of length L. The particle, if you're the particle, is stuck within that box. So that means that since the particle can't exist outside the box, there must be 100% probability of the particle being in the box, since it physically can't be anywhere else. That's it. You know, and I put it this way. I say the probability of finding the particle in the 1D box must be 100%. Because I think that that's the point, right? And if you're wondering what this whole psi squared with the absolute value sign squared, that's called the probability distribution. And I'm not going to prove the idea that a wave function when squared, or at least when multiplied by its complex conjugate, becomes a probability distribution. But the idea is that that's why I think that it's important just to remember this is just telling us that the particle must exist in this space because it's not allowed to exist anywhere else. Right? Okay. So all we're doing is integrating the probability distribution over the entire possible locations and saying that must be 1, because 1 is like 100%, right? Okay. Thus, we can get the normalized solution to the box Schrödinger equation. And by the way, box Schrödinger equation is not an official term, but I think that's kind of captures the idea, right? The Schrödinger equation of a wave trapped in a box, right? Matter wave trapped in a box, bouncing back and forth. And so the whole idea here is that instead of just having a general C in front, that C has become the square root of 2 over L. I'm going to show you where that came from in the first example, or the second example, excuse me, okay? Because that's what you're basically, all you're going to be doing in the homework is finding C's for different particular trapped waves, okay? All right. So I got a couple more things to show you because it turns out the way that I can really assign a variety of homework problems is to make this 3D, okay? Now, making it 3D might seem like a big step, but it turns out that it's not, as long as we stick to like rectangular solids. So let's get to that on the next page. Okay, so I have a picture. I'm going to be referring to it. This is my rectangular solid, in this case a cube. All right, so let's take a look at our new form of the Schrödinger equation. This nasty looking thing here, right? But if you look at it, it should look very similar to what we just saw. This is the time-independent Schrödinger equation for a particle in a 3D box, which is an infinite 3D well. Kind of weird to think of an infinite 3D well. How do you because maybe you can imagine an infinite, 2D well, just infinitely deep. But what does infinitely 3D deep mean? Well, kind of hard to visualize, right? But we're just going to draw it as a cube and just assume that the potential energy is 0 within the cube because there's no way out. Okay? Now, the form is the same, right? Because this is the second derivative of the wave function with respect to x, y, and z. This is the same leading coefficient, h bar squared over 2m, and it's still just equal to the total energy times the wave function. The difference is now the wave function is a function of x, y, and z. Okay? So it turns out that, there's the infinite 3D well, that the 3D solution to the box Schrödinger equation is just this. It's still just a sine function, except it's 3 sine functions multiplied together, each one being a function of just a single variable. So this is the sine function that's just a function of x, this one's just a function of y, and the last one's just a function of z. And it's the product of them, of the 3 of them, okay? And there's still some coefficient in front. This is called, right here, the normalization constant. That's the thing we can find for particular boxes, okay? So this right here is just the idea of the numbers of those standing waves, because just like our standing wave before that could have an n of 1 at the fundamental, the longest wavelength, now we have standing waves that are 3D, right? Good luck trying to draw that. I won't even give it a try, but you imagine there's some sort of standing wave in here, right? But it's a 3D standing wave, And so that that 3D, almost like a fluid, right, is trapped in that cube, resonating back and forth, okay? And then we can find its probability, and the probability must be equal to 1, okay? So and this should be integrating the probability over all the axes, which I don't make that as clear as I should have, right? So the probability of finding the particle in the 1D box must be 1. What I really should have shown here, and I think that I'll have to make a quick correction of this before I upload it, is I should have clearly shown that we're dealing with integrating it over that total area. Yeah, oh, I see. So it's not supposed to be equal to 1. This is the probability, and if we integrate it, then we're going to get it over 1. So what I can actually do before I upload it is just erase this 1, because its integral is supposed to be equal to 1. I didn't want to show its integral because it's a triple integral, which I just didn't want to quite go there. But the idea is that if we were to integrate it over 0 to L in X, 0 to L in Y, and so on, 0 to L in Z, then you'd have a total probability of 1. But the probability distribution itself is not equal to 1. It's just the integral of it over the entire confined space is equal to 1. I added this at the last minute, and it was a mistake. Anyway, so we got a couple last things I want to cover. These are not kind of the main focus, but I just want to make sure we're clear on them. This is the energy levels of the components of the nth standing wave. This is just like the quantized energy we saw for the 1D box. All right, I keep clicking the wrong thing. All right, then we have the total energy of the nth standing wave when L, right, because this is the individual components, right? But then the total energy, it turns out that we can get it to look like this, and it simplifies quite a bit when all the lengths are the same. So that would be for a cube. Okay, so this expression here is only true for a cube. But for another rectangular solid where the sides aren't equal to each other, like the examples I'll be giving you, then we'd have this expression here. Okay, so this is whenever the sides are not equal in length. Now, I actually don't ask you for the energy at levels. That would be kind of a follow-up question. It'd be fair game to ask like on the final, but it's in the particular homework problems I gave you, I just asked you for the normalization constant and we stopped there. Okay, but then once you had that, you could easily go back. In fact, you can find this without even finding the normalization constant. The normalization constant is only necessary for finding the probability of, say, finding the particle in like one region. So let me like draw like the idea, if I have, say, a smaller region, like, just the shaded region below this line, trying to make it look 3D, right? That lower, maybe third of the box, maybe this is the bottom third of the box along the z-axis, well, there's a certain probability of finding the particle in that section. And it turns out that that probability can only be found if you already know the normalization constant for your particular size box, okay? Or at least the particular ratio of your lengths of the sides. And also that probability can be dependent on the energy level, okay? Remember, on the quantized energy level. All right, so that's it for the presentation of the ideas, the key equations, and so on. Make sure that you look at the post notes as I upload them. I'll make the correction of just erasing the 1 here. And just kind of modify my notes slightly. But otherwise, we're all set. I'm going to upload this video, and then I will record a second video where I go over 3 examples. Examples 1, 2, and 3 of kind of increasing complexity, and I give you some tips on the homework. Thank you so much for watching.